First of all, we're going to talk about the quantum theory. Quantum theory is the foundation of modern physics, explaining the nature and its behavior of matter and energy at the atomic and subatomic level. Quantum physics and quantum mechanics are ways of describing the nature and behavior of matter and energy at that level. German physicist Max Planck presented his theory to why, as temperature increases, radiation from a glowing body changes color from red to orange and blue. He came up with a new idea that there is energy in individual units, just like matter. The idea became the first assumption of quantum theory. He eventually named these units of energy quanta. Quantum refers to clumps of matter and energy, while quanta is singular form of quantum. And next, I'm going to talk about the development of quantum theory.
In 1900, Max Planck came up with a theory that energy is made from individual units, quanta. In 1905, Albert Einstein agreed with Max Planck and theorized that radiation is also made from individual units as well.
In 1924, Lloyd Berkeley came up with the theory of wave-particle duality. The theory suggests that sometimes matter acts like a wave and sometimes like a particle. In 1927, Werner Heisenberg thinks that we cannot record the exact and accurate speed and position of particles such as electrons. This is known as the uncertainty principle.
So next we're going to be talking about the development of the quantum theory. The Copenhagen interpretation of quantum and the many-world theory are the two main interpretations of quantum theory's meaning for the nature of reality. The Copenhagen interpretation of quantum theory, introduced by Niels Bohr, states that a particle is whatever it is observed to be, for example, a wave or a particle, but that it cannot be assumed to have certain attributes or even exist until it is measured. In other words, Bohr was arguing that there is no objective reality at all. This applies to the superposition principle, which claims that although we don't know what state an item is in, it is truly in all possible states at the same time if we don't look to confirm. Schrodinger's cat theory. So Schrodinger's theory says that if a cat was put inside a box with cyanide, and the outcome could be that the cat could be either dead or alive. The cat could be pretty much dead, but it could also be alive because we haven't opened the box to check it yet. But when we open the box, there could be only one answer, either dead or alive. The multiverse theory. If you've been watching any Marvel movies lately, you've heard of the many worlds or the multiverse theory. The multiverse theory is the second interpretation of the quantum theory. It states that there is a possibility that there exists another universe where it is almost parallel to our universe, but some things might differ from our own universe. For each and every action you have ever taken, there would have been a butterfly effect that would eventually lead to the creation of a different alternate timeline or universe. Many scientists, including the late Stephen Hawking and Richard Feynman, have expressed support for the many worlds or the multiverse theory. The quantum theory's influence. Despite the fact that many scientists, including Planck and the legendary Albert Einstein, have disagreed with the quantum theory's implication during the last century, that the theory's principles have been continuously confirmed by testing, and even while scientists were attempting to refute them. Despite many scientists trying to refute them during the past century, the quantum theory and Einstein's theory of relativity are the two main foundations to modern physics. Quantum physics concepts are being continuously used in fields such as quantum optics, quantum chemistry, quantum computing, and lastly, quantum cryptography.
Okay, so now let's talk about electromagnetic waves. A wave can be described as a disturbance that travels via the medium by which energy is transmitted. As you can see in the picture, wavelength is the distance between two identical points on the consecutive waves. It is denoted by the letter lambda. Please take a look at the picture and you will see that amplitude is the vertical distance starting from the midline of a wave to its top. Frequency is the number of waves that pass through a specific point in a span of 1 second. It is represented by the letter nu. As you can see in the picture, the top one shows a higher frequency while the lower one shows a lower frequency. Here is a whole pictures of the wave components. As you can see, the amplitude is the distance between the midline of a wave to its top, and the wavelength is the distance between a crest to another crest. The speed of wave is calculated by the formula frequency times wavelength, and you can switch it around to find the other elements according to the pyramid that I have provided here. In 1873, Maxwell proposed a theory that electromagnetic waves are presented in visible light. Light waves are related to changing electric and magnetic fields. According to Maxwell, a changing electric field causes a changing magnetic field to change in time and space, and a changing magnetic field causes a changing electric field to change in time and space as well. Electromagnetic waves, or known as EM waves, are waves that are formed when an electric field and a magnetic field vibrate together. Electromagnetic radiation is the transmission of energy in the form of electromagnetic waves. Every forms of electromagnetic radiation travel at the same speed, which is the speed of light in vacuum, which is 3.00108 meter per second. As you can see in the chart that I have provided, each type of radiation resulted in different applications. So first, let's start off with the radio waves. Radio waves are used for radio and TV communications. They can travel great distances around the globe because they reflect off the ionosphere and the upper atmosphere. The next application is microwave. Microwaves are used to heat up food in the kitchens and also involved in how your cell phone works. In cooking, microwaves make water molecules vibrate and also generate heat, but do not penetrate the food to any extent. Next is infrared. Infrared is the first part of the spectrum that animals can detect. Humans sense this as heat. We use it to cook food and warm our home via a radiator. Other applications of infrared are TV remotes and heat sensing cameras. Next is visible. Visible is the part we are used. We can sense our world in full color because this section includes all the part which makes up the rainbow. Fiber optic waves guide that carry internet communication to our home also depend on visible lights. Ultraviolet. Most insects can detect UV light, but we can't. Ultraviolet can make a pale skin become tan via a sunbath. Energy-efficient fluorescent lamps also emit UV. A lot of detergents use optical brightness, which turns UV to visible light. This results in our clothes appearing brighter. Cancer are also caused by exposure to UV light because it damages cells. X-rays and gamma rays are both very high-energy waves that penetrate matter easily. Some applications of it are X-rays and CT scans and targeting tumors inside our body.
Information from Bohr's model. So electrons can only have specific energy values. Light is emitted as electron moves from one energy level to a lower level. So here is the model. From the model we have formula, so the change of energy equals to Rayburn constant, or 2.18 times 10 to the power of negative 18 joules times 1 over initial principal quantum number square minus 1 over final principal quantum number square. And here is another formula, which is E equals to hc over lambda. So it is E equals to radiation energy, h is Planck's constant, c is the speed of light, and lambda is a wavelength of radiation. Information from Bohr's model. So electrons can only have specific energy values. Light is emitted as electron moves from one energy level to a lower level. So here is the model.
Next, we are talking about Planck's quantum theory. When solids are heated, they emit radiant energy over a wide range of wavelengths. Different atoms and molecules can emit or absorb energy in discrete quantity. The energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiation. The energy of radiation is expressed in terms of frequency as E equal to h multiplied by V, where E is the energy of the radiation. H is the Planck constant, which is equal to 6.63 times 10 to the power of negative 34 joules second, and V is the frequency. Later, Albert Einstein also reinterpreted Planck's theory to further explain the photoelectric effect. The photoelectric effect was first mentioned by Heinrich Hertz in 1887 and Philipp Leonard in 1902. Later it was solved by Albert Einstein. He used Planck's revolutionary idea which states that light is a particle. The energy in light is contained in indivisible particles or photons. When the metal is exposed to light, electrons are released from the surface of the metal.
The quantum application that our group chose is microwave. An easy definition of a microwave is that it is a food heating radio box. It employs radio waves to heat food. Each machine that uses radio waves requires a different size of waves. A microwave uses a wave the same size as a computer hotspot. It starts with a power changer which converts power into the power that is better for producing a radio waves. Then the radio waves maker allows power to fly around in the spaces inside it. This helps build a radio wave of a specific size. The radio waves travel through the radio hallway and into the food box. The metal spinner changes the shape of the radio wave so that the warm spots, which have a strong wave, travel around a little. The radio waves heat the water inside the food. It does this by pushing tiny pieces of water to make them go faster. As the tiny pieces travel faster, it gets hotter, thus heating the food. The plate spinner circulates because the shape of the waves result in certain spots becoming warmer than the others. The plates spin to give each piece of food some time in the hot areas.